Hey everyone, welcome back to programming a Python 3 NES simulator from scratch. My name is Andy. Today we're going to keep on doing what we've been doing for the last couple of episodes, which is opcodes. The good news is we finished all the official opcodes on the CPU last week, which is really good. So now we're kind of up to unofficial opcodes. So what these are things that are not officially implemented on the 6502. Instructions that are not officially implemented on the 6502. But since there are 256 possible instructions, only around 150 of them actually have defined behavior, well defined by the CPU manufacturer. The other ones all do something though, and games use them, and so we need to implement them. So we're going to keep going on that. Now these unofficial opcodes are included in the NES test ROM, which is what we've been using to do our testing, so we're going to continue using them and just go like that. So yes, we've made really good progress, and now we just got to keep going. Now a lot of these unofficial opcodes are just combinations of previous things that we've done. So for instance, an RRA, which was the one that we're looking at doing next, is equivalent to an ROR and then an ADC. Which, so we've already done an ROR, we've already done an ROR and we've already done the ADC instructions, so this will just be combining two instructions in one. Cool. Another thing I want to look at today is speed. So you'll notice here that these all have something like 8 cycles, 5 cycles, whatever. So this is saying how many cycles of the CPU it takes to do one of these instructions. Now, if we look back at the NES CPU, we can actually see how fast it's meant to be running and therefore how fast we need these things to run. So you can see the, yada yada, blah blah blah. But the thing that we really care about here is CPU clock frequency, which is in the NTSC is going to be yada yada. Basically, every clock cycle is going to be half a microsecond. So basically, what I want to be doing is seeing how long it's taking us to execute some of this stuff. So let's do that. So we're just going to put some timing code in here. So back in our outer loop, and then let's do that. So right. So we're going to do it outside this loop. So we're going to add some timing functions. So start time is going to equal Python time function. We don't actually care about timing function. We just want to be able to do like a start and an end. So I want to know what the equivalent of time.now is in Python, because I've got no idea. Time it. I don't really want to do that. I just want to time does time vest time does clock. Yeah, whatever. Time.time. Cool. Okay. So time.time. We'll need to import time. Cadex, welcome back. Long time no see. Kind of busy with uni finals. Fair enough. How are they going? That's fine. I actually still haven't gotten around to implementing. I've still got it somewhere here. Implementing this this code that you wrote for loading the ROM header, because I'm still using the same kind of ROM, so I haven't got around to loading. We're not that far, but I do intend to come back to this and put this in at some point. End time equals time.time. And basically, at the moment, we raise an exception when we find something that we don't like, when we find an instruction that we don't know. So let's try this and accept, we'll just break. Print start time minus end time. Probably need to do end time minus start time. And screw it, let's just put a breakpoint here. Let's see what happens. So this is going to take a while because we're running in debug mode and we're printing out a lot of shit. So, but this will tell us how long that took to execute, which should be around a couple of seconds, I would guess. 2.5 seconds. Now, I believe that each one of these, so count equals 0, so how many instructions have we executed? Count plus equals 1. What were you doing? All the official instructions are done. Yeah, so in the last 4 to 5 seconds, I've just been doing instructions, basically. There's a bit more than that I've done, so I've tightened up everything else in terms of how the ROM works and how all the other things load in. We've got some memory mapping going. One of the big other things is that I'm now using this NES test log, which basically is an expected output of a ROM. So it shows you the registers and all this kind of stuff. And what it allows us to do is just validate that all the instructions are working. So I've used this I have something that parses this in using Regex and checks our expected output at every stage. And that's basically allowed me to verify that all the official instructions are working correctly. Yeah, and we finished all the official instructions. So now we're just going to do the unofficial ones, and then once we've done that, we should be good to go. And they should come a lot quicker because a lot of them are just combinations of official ones. Alright, so 2 and a bit seconds, and the count is going to be 5003. Probably a better way to do this is going to be to look at CPU dot PC reg, and let's get that as a hex value. Oops. So let's do a hex value of that. C6BD, and let's find C6BD. Now, yeah, okay, so the cycle count doesn't tell us anything. Alright, so we've done 5,000 instructions, and just kind of looking at this in general, you're probably going to be doing somewhere between 2 to 3 instructions a cycle, typically. Cycles per instruction. So if we divide, so we've done 5,000 instructions, which means we've probably done around 15,000 cycles. So count times 3, so that's how many cycles that we've done. And if we are meant to take 500 nanoseconds per cycle, a nanosecond, so 500 times e neg 9, 500 e neg 9, so that's 500 nanoseconds. So this is how many seconds it should have taken us, which is 7, I believe, is 7.5 milliseconds. So let's times that by 1e3. Yeah, so it should take 7.5 milliseconds, and we're taking 2.5 seconds. So we need to cut off, 1,000 times or whatever. So, I mean, most of this is going to be the fact that we're doing it in debug mode and that we're printing out everything. So let's get rid of that, and let's see what happens. We're doing comparisons. So get rid of the comparison, and in the identifier, let's get rid of the print function. And let's see how far off the pace we are. And the answer is, yeah. The answer is it's taking us 277. So let's times this by 1e3, and this will give us it in milliseconds. So we're taking 300 milliseconds, so we're around 100 times off the pace, which is probably what I expected. So we'll need to do, which is fine, because we haven't done anything about making this faster or optimizing at all, but at some point we'll need to come back and make this faster. Nice, I haven't mentioned any of the rad parts yet, like the APU, PPU. Yeah, that's going to be the rough stuff, I suspect, but for now, CPU instructions are the thing that's going to be eating up some more time, but we're getting pretty close. Alright, so we know that we are slow at the moment, but that's fine. I just wanted to check around how slow. And the answer is we need to do some optimization work at some point, but I'd rather get it working first and then come back to it. Cool. Alright, let's keep going then. So what instructions are we up to? My, emulating the CPU cycles. No, I'm not actually at the moment. I'm just doing, I kind of do like a rough benchmark of how far off the pace of performance I am, which I think that calculation is correct. The CPU cycles is the one thing I haven't done actually. I guess the answer will be just run as fast as you can and let's see what happens. Maybe it needs to rely on a fixed clock cycle or something. But I don't think there's any pipelining in this. So as long as I'm running the instructions sequentially, I suppose it should be fine. Maybe. Let's find out, I guess. Alright, so running the test ROM instruction not found. 04. So now let's get rid of this stuff. Let's find out what the 04 instruction is. Zero 04 is a not. Let me just check that I haven't made any changes here. Yeah, I'll just reset this. Reset. And then let's go. Yep, instruction not found 04. So the 04 instruction is going to be a NOP Z package 3. Alright, so we have NOP operations, but apparently they're going to have different modes of operation. So we need to add a Z package mode to the NOP. So let's find our NOP operation, because I have no idea where NOP is. And it'll be in here somewhere. Yep, so we've implemented a NOP, which just does nothing. Clearbit. NOP. Nice. So we only have a NOP implicit. One of the other things that I've been doing actually, KDX, is trying to do, so for something like jump instructions, you can see I'm implementing it in the same way. But for load instructions, I've started doing some dodgy stuff. So basically I couldn't be bothered typing out for all the instructions all the different addressing modes. So I basically have just created something that can parse the documentation of what all the different instruction types are and generate classes automatically based off that. So it reads in whatever this is, gets the correct type of addressing, reads in the opcode, reads in the type of thing, and turns it into a instruction class. Yeah. Hopefully I can manage to do more NOP type instructions. A man can pray. But the problem with this kind of stuff is that it's not listed in these pages here, which is really annoying, because basically how I've implemented everything is just like copying this documentation and auto-generating it. So yeah, sadly I'm gonna have to do this a bit more manually, unless this has one that's on unofficial. No, you spelled immediate wrong. So while you were technically correct in that it is spelt wrong, it was actually not me. It is this which site is it? This 6502 instruction site, which is where I copy the documentation from and use it to auto-generate it, is the one that has misspelt it. But I kind of kept it there because I couldn't be bothered fixing it. So I just copy and paste this in and it generates all the different types of addressing for me for each instruction. So blame etradition.net for making a spelling mistake probably around 20 years ago. Alright, so let's do some more NOPs. So what are the NOPs? Oh god, so there's so many NOPs. Jeez. So I don't really want to type out all of these. So what I'm going to do is do the same thing I did before, and I'm going to copy this into a table, unless they have some tabular form themselves. NOP EA, NOP do. No, they do not. So what the format is, so let's open up load instructions. Let's look at the format. So I kind of want to copy this. I want to copy this into NOP stuff. And let's just define these manually. So a lot of these look like they are all using the same thing. So we can pretty easily define this here. The only thing I worry about is getting it in a nicer format than this. So does this thing, programming with unofficial opcodes, nope. Okay. Yeah, okay, so it's saying there's a lot of NOPs that, there's 6 unofficial NOPs, jeez. And this thing is telling me that there's a lot of unofficial NOPs. Ooh, yeah. Okay, so one thing I have been doing is downloading some files that might allow me to, let me just find this, and the name is going to be have NES. Let me just search for this. Instruction timing. PCB. So the reality is that there's going to be all these different sources of documentation. Yeah, this one. So here's a NOP. Yeah, the quirk is that these undocumented processes, opcodes did something. Nope. 12 is stable, and match should be used. Alright, well, let's find if they define what these NOPs are. Illegal opcodes. Most emulators just treat these like NOPs. Ooh. Interesting. Yeah, so there's a lot of NOPs that we can put in. The question is whether we treat other unofficial things like NOPs, because I know that that might not be what we want to do. Anyway, okay. I'm just going to copy this manually. So we've got a lot of NOPs. Geez, 33, slightly less. So that's going to really fill up our table. Now, where are the CPU unofficial opcodes? Is unofficial meant to be a NES thing or a CPU thing? It's a CPU thing. So these are the 6582 CPU unofficial opcodes. And most NES games don't use them, but if I run the Super Mario Brothers ROM, it seems to hit one quite quickly. Now the reality is that that maybe comes straight after a jump instruction. So I think that my jump instruction might just be off by one. But to test that, I kind of need to keep going through this NES test ROM, which validates all the instructions, and to do that, it tests the unofficial instructions. So I kind of need to implement the unofficial instructions so that I can test that the official instructions work correctly, even though they might not be present in the ROMs. Yeah. Anyway, so 04. Yep, so we're going to just verify that this is a NOP. Yep, there's a lot of NOPs. Alright, so this is actually going to be really easy to do. So I'm just going to do it. So my instructions here. So we don't actually care about this. The only thing we care about parse out of this string is this thing here, which is immediate, or the type of addressing, and this thing here, which is the opcode. So what we're actually going to do is, just to be clear, say immediate. There's going to be Z package, ZPG, operand. I'm actually going to come back to this site, 6502 instruction set, and I'm going to copy a 0 page thing, and I'm just going to use this as an example. So 0 page, and it's going to be a NOP operand, and the opcode is going to be 04. Yeah, 04. So now, in the same way that we used load instructions, so we've got to define a types at the top of the file, we basically got to store what these classes are when we generate them. So I've got a helper function that'll just help me do that. So let's import that, and we're going to be generating NOP instructions, and we're going to be using our NOP types function definition up here. So let's also define this one, which was implicit addressing. So if I come back to this thing, and I go to my NOPs, I can see they call implicit implied, but it's the same thing. So this was the, this will generate, this line here, when it goes through its helper function, will generate this NOP class. So I can just delete this now, and we should get up to the same point, except the next NOP operation should work. Keyword error implied. Right, so this helper function needs to define implied, which is just a naming thing I call implicit addressing, because I'm not a very smart man. I'm just going to refactor this and rename this to implied. There we go. Right, so now, oops, we want to run the test ROM. And the test ROM instruction results not expected. Right, so now that our NOP 0 page is doing something that we don't expect. So let's go look at this, and we can see why. So NOP 0 page. So basically I've written something that validates everything here, and what we're saying is that the instructions don't match. So the expected instruction is a NOP, star NOP. Yeah, okay, so this is going to be a, the reason for this is that this NES test log must use star NOP to indicate a unofficial command, which we don't really care about. So we're going to go back to our Regex parser, and we're going to try and figure out why it's not giving us the star, which we don't want. I was just about to compose a oh, that's sad. Just kidding. Okay, well that's slightly better. I think the these, I don't know what the other one is, 6502 and eTradition haven't been updated in around 15 years, but they're still completely relevant today, so credit to whoever made them originally. And what is my, let's look at my validator. It's in nesttest.py, and my pattern is this. God, so you can see why this regex thing took a while. So we want to take it for 8 characters, then as many spaces as possible. Right, so if we go to here, is there any, instead of going for 8, we should just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We should just go for 10 positions. And then 11, because 11, we don't need any spaces. 12? Nope. Right, so we want to go, what happens if we go back to our original thing? Right, so we come here, we have as many spaces as possible, we capture the next 8 characters, then as many spaces as possible, and then the next 4 characters. So really what we want to do is make sure that this length here which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 characters is captured nicely. So if I up this to 9, it'll match all the way up to just before the star. If I take this out, that's going to be fine. And then add 10. So if I add 10, it starts going backwards. Any amount of spaces is where it gets weird, because I don't want this star to be caught by the first thing. So let's just get rid of anything that goes on here. Debugging, cool. My internet is horribly slow. Here we go. So where is my test data? So copy that in. Where is my expression? Alright, sick. So we match the first 4 things, then any amount of spaces, then what does this do? Oh. Alright, so I want to start at the start. JavaScript, Python. I don't know what changes that makes, but cool. Alright. So what happens if I do this? Yep. I'm now going through the spaces. How do I tell which match this is? Right, so it matches up to that point. Then group 2 9 times. Let's make this 8 times. Right, okay, so group 1 is now... Right, so group 1 is CBD, then group 4, group 2 is 6 to 14, group 3 is 15 to 19. Yeah, interesting. Is that where it stops? Ah, so each one of these dotted black lines is... it's found it again. Okay, so let's just pull it back to here or something. Cool, okay. And now, I'm going to highlight here. I don't want that group, I just want this group. Yeah, okay. So C6BD, and then we find 04A9, and then we find star knob. I don't know why we find star knob now. Okay, I do. So we actually don't want this to have any spaces, and we just want this to be a fixed amount. So 9. Yep. And if we go up to 10, is it still matching our spaces? It includes the star now. Yeah, so I think we want it to go 9 characters and then take one of anything. So 9 characters, one of anything, whether it's a star or a space, and then 4 characters to capture. Yeah, I think this is what we want to do. So if I come back to here, to our NES test, I'm just going to copy and paste this in. That's horrible. Was up to around there? Yeah. So let's copy and paste this back to Regex land. As many spaces as possible. The next 9 characters, then the next 4. Yeah, so it's still not working. 4 characters, many spaces as possible. It's not working. Let's chuck all this stuff out. Yeah, so that works. So let's just like lop things off until it works. So does that work? No. So I think because I probably offset things by 1. No, that still doesn't work. Now it works. Right, okay. So before I was taking these 4 characters, and now I'm taking these 4 characters. So if I just remove that space, now it works. God, Regex. Okay. This should now work. I'm also going to turn this printing off, just because it doesn't really do anything anymore. Instruction not found 4.4. Cool, so now we get the thing that we expect. So let's go back to instructions and let's start adding more of these NOP types. If you work on Regex 101, make sure you set the Regex engine on the left. You're currently using PCR, which aren't equivalent. Oh, good. Okay, cool. So it looks like it's returning the same result there, which is good. Yeah, so this has worked for me up until now. It's just this star was something I didn't account for. Let's come back here. Let's start adding more NOPs. So 0C. And now I believe that 0C was absolute. Okay. So let's copy an absolute instruction and turn it into a 0 page. So turn it into a NOP, and the instruction was 0C. Cool. NOP. So we got a Z package X. 0 package X, sorry. Yeah, which we'll copy from here. It's a NOP. And the instruction is 1.4. Whoops. Alright, the next NOP is going to be just an implicit NOP, which is going to be 1A. So we'll have another implied NOP. So it's going to be the same thing, except it's going to be 1A. We'll have another one here, which is going to be NOP absolute X. Yep, so we'll go capture an absolute X type. Do the same thing. Turn it into a NOP absolute X. And what was the thing that it was? Is 1C. The next NOP is going to be 3.4, and it's going to be a Z package, 0 package X, which we've got. And it's going to be 3.4. I get the feeling there's going to be a bit of mirroring down this row. Now I believe that this thing might lay it out in a way that's more intuitive. Yeah, it does. So let's use this one instead. Yeah, so these NOPs are spread around, you can kind of see. But then they arrange them in a different way down here. Yeah, so you can see the NOPs are arranged into columns and rows and this kind of stuff, which seems like it's going to be really good. So let's do this this 4 row. Well, let's do this row. So 8.0 is going to be a hash I. 8.0, which is an immediate. So let's find an immediate, a misspelled immediate, but an immediate nonetheless. I'm going to change all these NOPs at the end, and this is going to be 8.0. Cool. So we've done that one. Let's do this row, so the 4 row, which is all just going to be Ds. So 0, 4, which we've already done, is going to be 0 page. So 0, 4, 4, 4, 6, 4 are all going to be the same thing. So 0, 4, 4, 4, and 6, 4 are all going to just be 0 page. Then 0C is going to be A. We can find out what that means. We've already done that. That's absolute. Cool. So we've done them. Nops. There's more in here in the 1, 4 column. I imported a 12-pack of ginger brew. I love it. Ginger brew, presumably being a beer? Like a ginger ale? Ginger brew. Let's check it out. Is it alcoholic or is it sick looking video? Ingredients: sparkling water, fresh on the road, non-alcoholic. Right, so more like a. I don't think ginger beer is alcoholic, right? Yeah, I'm Australian. To me, yeah, I think ginger beer is non-alcoholic. Ah, flavors. That looks sick. How much does it cost to do? Yeah, it's non-alcoholic. How much does shipping cost? I might get some. Get out of here, Regexes. I heard it's pretty popular in Australia. I've never heard of it. Doesn't mean it's not popular, but. Alright, 1 4 column is going to be DX, which is going to be 0 page X. So it's going to be these ones. So we've already got 1 4 and 3 4. We also need 5 4 7 4. Okay, so let's just keep going on these. So we need 5 4, 7 4. Geez, what's this? D4 and F4. Down in this column, which is going to be the 1C column, we've got absolute with X. Yep. So we start off at 1C, which we've got. Then we're going to end up at 3C, 5C, so on and so forth. So let's copy some of these. 3C, 5C, 7C, DC and FC. Alright. It's actually pretty cheap. Paid 15 euros for a 12 pack. You're more into lemon bitters. Presumably Australian if those Australian girls telling the truth. They never do. Nah. Lemon bitters is nice. Depends where you are in Australia. I think that kind of stuff is more popular in the northern parts of Australia, i.e. where it's warmer. Your Queenslands of the world. Basically, the closer you get to the equator, the more people drink nice drinks. Down here we tend to drink Coke and stuff that's bad. Nop is going to be 9.9. Nop immediate? Yeah, okay. Which is going to be 8.9. So this is going to be 9.9. Any other nops? Oops. Yep, so we've got another couple of these here, which is going to be on the 8.2 column. Oops, this is going to be 9.9. That's not good. So let's go back to here, and we can say 8.2 is going to be the same thing. 8.2, we've already got 9.9. What's this? C2. And E2. Are there any other NOP immediates? Nope. Okay. And what do we got left? We've got a normal NOP at EA, which I believe that we already have. Yep. And then we've got normal NOPs all the way down the 1A column, right. So these are normal NOPs. So we've already got 1A, and then let's chuck in a few more, because we're going to have 3A, 5A, you know, so on and so forth. 3A, 5A, 7A. And then DA and FA. Right, so that should be all the NOPs. And if I count these, can I just count them by doing this? 28 lines. 56 matches. 1, 2, 3. Yep, that seems right. So 28 divided by 2. Sweet. Right, so now we've done all our NOPs. Okay, so we have failed our instruction match, which is the classic things that we seem to do. So our expected instruction is a NOP, and our actual instruction is a load immediate. Interesting. So what's our data bytes match? Oops. Self.expected bytes is 89. Sweet, indeed. Let's think about this. So that was just like 30 more instructions. So you can see these unofficial instructions aren't going to take as long, because we can just, if we just did another 30, then we just increased our instructions from 151 was where we started off to 177. And we've got to go to somewhere near 255, so it'll get a bit quicker. Right, okay. So what is our PC reg? And let's just put a breakpoint on that. cp.pcreg 50,922. So let's copy that value. Let's come into here, identify. Yeah, we basically want to put a breakpoint here when self.pcreg is equal to that. And cool, so what's our identifier byte? 80. And our instruction is LDA immediate. Yep, so that's what we expect. Ah, right. So we expect it to be a NOP, but we say it's an LDA immediate. Okay. 80 is meant to be a NOP. Right, okay. So let's look at our LDA immediates. And do we have 80? Control F 80. Continue. Do I need to copy NOP into all of these? I mean, it shouldn't matter. 80. What is our identifier byte? I swear you have one fewer picture frame. I think I may have just moved the camera slightly to the right, which means that it has revealed another beautiful painting. Oops. Okay, let me just unplug my phone. That's going to get annoying. Yeah, one more. Oh, one's hiding behind my head. So I have 3 up on the wall. paint a few more on this wall, but that would involve some webcam trickery that it's going to be a bit difficult. Alright, so let's look down for instructions, and we want to find self.instruction identifier byte. Well, let's go down to this line then. Let's find out what this returns. Yeah, is a not immediate. Okay. Ah, so it works. Oh, it must be on the next line. Yeah, shit, okay. Right, okay, so we fixed that. And we expected a PLA, and we got a not immediate, right, okay. So what is CPU dot instruction? Okay, so if we look at the CPU, how do we identify, based off the identifier byte? I'm going to store this identifier byte in the CPU. Refactor, pull members up. Nope. I believe move extract variable. Nope. Extract field. Replace all 5 occurrences. Haha! Initialize in constructor. And we're going to call it self.instruction byte. That is cool. Yep. And then we'll just define it up here as none. So now when we hit this breakpoint, where am I? Actually, yeah, you move the camera. The corner isn't showing, yeah. The skateboard's still there. If you can see it. In my skateboard corner. Self.instruction byte. Cool. So let's keep going. And now we can do CPU.instruction byte is 80. Which means it's not immediate, and we expected it to be a PLA. So now I'm confused. 80 is definitely meant to be a NOP. Eight zero, yeah. Okay, so what's our .pcreg? Let's put this in hex and let's look at the C8OC. Yikes. Okay, so what is the loaded line from self.line from here? So C70C. Okay. Right, okay, I'm going to bring back this print function. Oh yeah, instruction byte, sure. Right, so now we're doing a lot of NOPs. Which is what we expect. NOP implied, NOP implied. Still a lot of NOPs. Right, okay. So let's find this BNE. So this is probably what's gone wrong. Right, so we did a branch and we expected to end up at C70C and we actually ended up at C80C. So that's what's going wrong here. Is that we, yeah, right. So our jump is wrong. Our BNE is wrong. Because our program counter is wrong. And if I actually looked here, data bytes match, instruction bytes match, and the PC doesn't match. Yep. So our NOPs now work, but our jump is wrong. So let's look up this BNE and find out what it is that's wrong about it. So it's a D0. D0, which is going to be a relative BNE. So let's look up our jump instructions. Let's find our BNEs. Branch clear. Wait, what? Oh. So branch on result not 0. So we branch on Z equals 0. And the only method is relative. Okay. So let's jump back to our previous instruction, which was C27A, C27A. So we've come from C27A. So let's go back to the CPU. Let's set here when self.pcreg equals this hex value. Wait a minute, now it's... Whoa. Do I have something that's not behaving consistently? SGA not immediate. Now I'm confused. Whoa. Now I'm really confused. Have I changed anything? Implicit. Yeah, just refactoring. Importing. Change the pattern, but I don't think that's it. Nothing here, nothing here. Added a whole heap of NOPs. And, yeah, just renaming. Ooh la la. Now it's breaking at a different point again. Alright. Now I'm confused. Oh no, this is back to the original breakpoint. 80C, yeah. 80C. Am I crazy if I set a breakpoint here? That's changing my results? It is. What? That's not good. I'm not doing any multi-threaded stuff. What? Okay. So where am I up to? I'm up to around halfway here. Around halfway here. C7-2A, yeah. Versus way earlier. 19D. I expect to get an STA, and I actually get a NOP from 99. This is weird. Alright, so 99 really should be, yeah, store accumulator in memory. So why did I think a 99? Do I have a 99 in here? I do. Immediate. I must have been wrong. I have no idea why this is only caught on a certain thing. But, yeah. So it should be 89, not 99. That is very worrying. So I believe this is 99, I kind of want something where that'll pull that out for me. So for instruction in instruction list, so let's see, let's throw an arrow if we have. So if instruction duplicate, right, so we kind of want this. Want to find instruction dot identifier byte is in self.instructions and self.instruction.keys. So now this should throw, yeah, okay. So let's breakpoint here and let's check that it's throwing on 99, not immediate. If I change this to 89, it should now pass. Cool. So interestingly, that thing only threw at a certain point. I have no idea why that is. It's bloody weird though. Oh well. Right, so now we're at this breakpoint and our instruction byte, self.instruction byte, is going to be D0, which we would expect to be C0. That's way too hard. D0 to be a BNE relative. Yeah, this is what we expect. So we want to find the instruction. So the instruction should be a BNE. If we've got it, get the data bytes, print. We basically want to come down, we want to compare, it should pass, then we want to execute. I'll get into here, want to jump in. So the memory address, alright, let's just go. Never mind this. So we're back to here, and we know that our next instruction is wrong because we've jumped to the wrong place. So we do want to grab this. I want to put this down here. And then we want to jump into this BNE and we want to see what value, what's going on. So jump in. So we're using relative addressing. So the current address is something. 50,988. Yep, and we're going to return whatever this is. And let's put that in hex so that we can see. So this should equal 7C, but it's actually equaling 8C. Cool, so why is that? Now the reality is probably because it's wrapping around a page or something, but let's find out. So what's the current address in hex? So we start at 72 C272. Wait a minute. Current address. Right, so it's this one that we're looking at. So we started at C7-2A, but then we've incremented since then. We might need to increment -1 or something. Anyway, so this is saying it should go to C70C, and we're saying it goes to C80C, which is clearly wrong. So we start at C7-2A, I think. Or you could argue at 2C. They're quite similar. They're only 2 apart. So that's not going to be the value because these things are widely apart. So the difference is going to be what this value equals. What does this equal? 224. So my guess is absolute addressing can only go 250 or 128 bytes in each direction. Absolute. So to do this, let's do, there's a skill direct page. Let's go to this and let's look up how absolute addressing works. And so that'll be my suspicion about why this is wrong. With absolute addressing, the full, wait, what? Oh, the full memory location. Okay. BNE. Absolute. Oh, must be relative. It's D0. So let's look at this table. D0, relative, right. And the answer is relative. These instructions take a single byte, which is used as an offset from the following instruction. Right, so you can only jump down, but it'll only take a single byte. So I think if I do, instead of uint16, I cast this to a uint8, which means it can only go up to 256. Oh, it equals the same thing. Shit. Huh. Okay. So let's go back to here. What do we need to add to get to the desired address? So the current address, and what's the address that we want to go to, is 0xC70C, I believe. C70C, yep. And what is this? Minus our current address. We want to go backwards 32. Yep, so it's going to be signed. So we need this actually to just be an int 8, I believe. Yep, that's correct. Signed 8-bit value. Ah, can only jump 128 bytes in either direction. There you go. In the comment. Cool. So this should work now. So our BNE was wrong. Instruction not found A3. Cool. So we can go back to here and just verify that A3 is an unknown instruction. Yep. At this table, A3 is a LAX. So let's find out what a LAX is. So shortcut for LDA value and then tax. Save a byte and 2 cycles and allows to use the X-reg or whatever. Notice that the immediate is missing. The opcode that would have been the LAX is affected by line noise on the data bus. Even the bugs have bugs? Oh shit. Alright. Yeah, okay. Sure. So let's find our LAX. So it's an LDA and then a tax. LAX. Yep, and in this, yeah, so it's all in this one row. So it's all A3 blah blah blah. I'm going to create a new file called combination instructions. And let's copy from load instructions. Let's just do this, because that's how I roll. Right, so types, lax types, and we want to get lax. Import that. In the CPU, we're going to need to import this new file, C file. Right, and so we just need to define lax. So let's go to our base instructions file, and we know that a lax is just going to be lax, going to inherit from instruction, and it's going to be a combination, where was it? LDA and then a tax. So an LDA does this, and then a tax, then a tax, TAX, and then a tax. Right, so I'm going to have to put this LDA, then tax, so let's do it here, which is going to be an LDA, then a tax. Register modifier does the same thing. Cool, so let's just do an LDA, then a tax. So both LDA, if we look at LDA, just uses the write function, and tax is just going to use the write function. So an LDA and then a tax is just going to call both of them. Now, depending on what kind of things that it's using, though, shortcut for LDA and then tax saves a byte and 2 cycles, allows the use of the X register with the DY addressing mode. Jesus. Okay, so we want a very specific thing. LDA and then tax. So LDA, this is weird. So we kind of want to make an LDA instruction and then just call execute on it. And actually what we want to do is put this in combination instructions, where it should be okay. LDA then tax. So the write, actually we just want to overwrite execute. Can we just do that? And we want to create an LDA instruction. Import CPU C. LDA instruction, and then what was the other one? A tax instruction. Here's going to be the issue. We need to determine what type of addressing each one of these things uses. LDA. So an LDA DX is a 0-page X. So let's presume that LAX with something, 0 page X. So maybe the easiest way is going to be do this is going to be 0 page X. Then we can call our load A 0 page X. Oh god. So where are my load instructions here? So the load A 0 page X function is defined here. Since we auto-generated it, it's going to be a real pain to get to it. Alright, so this is going to be more difficult than I thought. This is going to be a downside of the way that we've done it and auto-generated everything. So we need a load A 0 package file. Let's just go to this shit and then just say identify byte. Okay, so if we just do A for absolute, byte start from hex AF. No, we can just do bytes. So now this should get imported and we should hit this. Let's see what happens. LAX is not defined. Right, yeah, okay, so I can just comment out all this stuff. Instruction not found, A3. Right, okay, so we need the A3 one. LAX 0 package X. Okay. Did it call this function? LA 0 page X. So what's my cpu.pc reg, or what am I up to? So let's set it here. And self.pc reg equals this value. Want a breakpoint, and we'll see where we go. Raise exception. Yeah, okay. Ah, so the load A immediate is the thing that's not working. Even. Oh no, data bytes matching. Right. Data bytes match. Self.expected bytes. CPU.data bytes. Yeah, okay, because this instruction doesn't define the right stuff. So if we do load A with 0 page addressing with X, it should work now, and it should hit this breakpoint. Yeah, sure. Yep, it does. Okay. So we want it to do, so it's already, if we do it this way, it's already done the LDA. We'll execute Yeah, well, this will just get us the right data stuff. And we actually just want it to execute the LDA instruction. So cpu.execute CPU data bytes. And then we kind of want it to do a tax instruction. So the tax instruction is going to be a bit more difficult, where we just need to define a tax. So where's the tax instruction defined? I can't remember. Tax. Say import tax. And data bytes. So that's kind of what we want to do. So we want to do an LDA and then a tax. Yeah, I think that works. Unsupported thing for something. Right, and the reason for this is that we're going to need to return the result of the tax, presumably. Nope, we're not going to need to do that. We're going to need a, so where's instruction? It's going to be in generic instruction. So we've executed this thing. We've executed this thing, and then we return the value. Alright, let's see what's wrong. So our A match is wrong, our P match is wrong, our X match is wrong. That's a lot of things that are wrong. Alright, load and then tax. And what does a tax actually do? Sets the X reg to be the A reg, and the A reg is wrong. Right, so let's find the CPU dot A reg. So we just actually need to call the tax.write function instead of executing the whole thing. And we actually just need to do load a dot. Yeah, we should just do the whole thing. CPU data bytes, whatever. Okay, so I did execute. So what's our A reg and what's our expected A reg? 85. Alright, so let's go to here, let's breakpoint, and let's see what happens. Jenny's gotta go. Load. So, we're inside the load A now. The memory address is 67, the value that we pull out is 128, and then we want to write 128. And what we're saying is when we hit here, CPU average, and we expect it to be 85. Okay, so if we expect it to be 85, let's just check that out. LAX. Nope, this is not the one we're looking for. Let's find what my PC reg is. Expected PC reg. Let's find the hex of that. Copy value. Control F, paste, bam, 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 bam. E. Right, okay. So we want to load in the value of 0, and then we want to do a LAX, which should return 55. which is 85, yeah. Right, so we load that. So the value of A before this instruction should be 0. And then we want to be loading in from 40 offset by X, and the value of X is 0.3. So we should be getting it from 43. So let's go back to this thing, which is this 43, and it's saying that it should be 0580. So CPU.get memory from 0x43, which equals 128. Yeah. Load X. So 0 package with X. I believe. 0 page, I should say. 0 page address is given, and then the value of the X register is added. Yeah, so the value that we should be looking up is whatever's in 43, which is what we do. And they're saying that equals 0580. Whoa. So what if we just did a base instructions, a bit instructions, combination instructions? Did I close that file? No, it's right here. So what if I ignore this and I just did this? 0 page addressing with X and an LDA instruction. So this should just load the A instruction. It should do a load A. So A match is false. And the reason for that is still that we have the wrong value in memory. And the reason we have the wrong value in memory is that we pull out 128 when we expect it to be 55. So we load 0 into the A register, then we load from 40 offset by 3, 43, 0580. LDA is not, 0 page is not offset, right? Load this into the A register. The expected A and what our actual A is 128. So it looks like our memory is wrong. Unless I'm misinterpreting this. Regardless of the fact that it's an LAX instruction, the memory at 43 should be 55. And it's definitely not. It's 128. So, yeah. So let's find out what's setting this. So set memory. So let's use a breakpoint here and let's do location equals 0x43. So when do we set the memory at 43? Once, okay, so we set it just before, which is a store A0 page. And we get passed in a value of 43. And the value of A is 128. That seems right. What's my thing? E52A. Yeah, so it's this one. So we store the value of A, which is 80, which is 128, in the A register in 43. And then we load from 43. So if we're loading from 4.3, it should equal 128. So my thought is maybe this LDA LAX thing is slightly different. Shortcut for LDA value, so an A3 is a DD. A3 DD. A3 IZX 6, which is presumably, right, A3, let's look here. LAX DX, which I'm pretty sure. So if we look, IZX6 is going to be the same instruction mode as A1, which is a load instruction, is indirect. That would explain a whole hell of a lot. Indirect ZX. So I have merely just misinterpreted what this thing is, which is a NOP. Right, okay, so D actually means indirect here. That's kind of frustrating. DX. Ah, the brackets. Ah, shit. That's what the brackets mean. Okay, that's that is useful to know. Alright, so we actually just want, coming back to my combination instructions, instead of 0-page addressing, we want indirect addressing. So let's just come down to here and copy that out. Indirect addressing with X. Is A3. And then we want to execute that and then return whatever the value of that is. Now there might be a better way of doing this. Yeah, we don't care. Instruction not found, A7, perfect. Okay, so this works. It's not a great way of doing it, because we are recreating this load A indirect with X class, which already exists. So let's see if we can do this a bit better. So from instructions dot bit instructions, now we want load instructions import load A. So base instructions, let's open load instructions. Can we do import types? Let's get rid of this types. Can we put a breakpoint here? Right, so types is this, and we want the class. Right, so we want class here, which is lax indirect x, lax int x, which is just going to be an instruction. That uses indirect addressing with X. No, I actually think this is going to be the easiest way to do it. Bam. Right, okay. So that's one way of doing it. Let's implement all the other types of laxes. So I'll just copy and paste this in here. Done. Done. So we've got indirect X, which is good. we've got, which is load A, then tax. We could do a base class just called super.execute, and then returns tax.execute. And potentially you just pass in, so let's do class LAX, which is going to be an instruction. Well, it's just going to be nothing, I think. Def LAX, whatever. Class CPU, and then data bytes. And instead of calling super, we can just call load A class. And now here, this can just call lax.lax, CPU, data bytes, and super. And it should just return that. Cool. Yeah. It's probably a terrible way to do it, but whatever. Don't really mind. So LDA, we also need an LDA 0 page, which is just going to be 0 page addressing. So I believe that's what the D means. So let's just check that this time. So nop D. Actually, let's just find an official one. So 2.5. Let's just go to this table. 2.5 is 0 page. Yep, so D means 0 page. It is just going to be A7. Then A is going to be absolute. And absolute addressing is just going to be AF. Yep, let's copy that again. Absolute, indirect. Indirect addressing. And indirect addressing is going to be B7. I've missed one. So it goes absolute, then indirect with Y. So LAX indirect with Y, which is just going to be indirect addressing with X changed to Y. Instead of AF, it's going to be B3. And then lastly, we're going to have, I'm so confused, 1, 2, 3. So we've got indirect with X, 0 page, absolute, indirect with Y, then 0 page with Y. Right, okay. B7 is 0 page with Y. Zero page addressing with Y is B7. Yep. And then lastly, we've got LAX, which is going to be absolute with Y. Which is going to be BF. Done. Sweet. Okay. Instruction not found 8.3. Yeah, okay. So 8.3 is going to be a sax. Stores the bitwide AND of X and Y. As we store A and store X, no flags were addressed. As soon as I've done this, I just kind of get the feeling that I should just implement this properly. And I'm going to do it. Yeah, okay. That was a waste of time. So we've got a load A, and then we've got now LAX, which is just going to inherit from a load, which means it's going to do these things. So it's going to do the CPU reg, and then also set CPU, so LAX. Does a tax do this? Sets the xreg to the areg. So xreg equals CPU.areg. And it's going to return whatever the default is, which is just going to be the value that we're writing. Yep. Cool. Alright, so this is just a LAX instruction. This is way easier than doing this shit. Alright, where's my load instructions? I am not a smart man. LAX types, LAX. And this LAX types should just return Yep, so let's just override this. So there's no immediate. Is there a 0 page? Yes, there is. It's A7. Yep, so this one's wrong. Gone now. We have an absolute. So we've got a 0 page. We've got an absolute, which is going to be AF. We've got an indirect with X, which is going to be A3. We've got an indirect with Y, which is going to be a LAX indirect with Y is going to be B3. Then we've got a 0 page with X. No, this one's going to be 0 page with Y. It's going to be B7. And then lastly, we're going to have an absolute with Y, which is going to be a BF. Right, instruction not found 8.3. So this is going to be saxes. A sax is a bitwise AND. Right, so let's do LAX. Let's go back to here. LAX is load A, then tax. And the next one is going to be sax, which is going to be somewhere in here. Sax. So it's not going to do any of this stuff. And it's just going to do a store A. Writes to mem. And it's going to store the bitwise AND of A and X. The bitwise AND CPU.xreg. Right, alright, combination instructions. So we're doing sax. And what are our sax types? So there's a zero page, there's an indirect with X, which is a sax, and that's going to be 8.3. We've got a D, which is just a zero page, which is going to be 8.7. We've got an A, which is an absolute, which is going to be 8F. I feel like there's a common theme here, and then dy, which is going to be 0 page Y, which if I had to guess, oh no, it's going to be 9.7. Let's keep going. Next instruction results not expected. Cool. So what doesn't match? Instruction match. Okay, so what's my expected instruction? Sax, and what's my actual instruction? Is a LAX. Alright. What's the CPU.identify or instruction byte? 9.7. So 9.7 should be a sax, but it's actually a LAX. Why would that be? Import sax. Am I doing this the wrong way around, potentially? Yeah, okay. I don't know why that would happen. Probably because I parsed this or something. Alright. EB. E. B. SBC. Watermark instructions. Other instructions are equivalent. Okay. (6.9) and E9 are official, EB is not. These three opcodes are nearly equivalent, except that E9 and EB add 255 minus I instead of I. Have your preprocessor choose randomly one of these opcodes. SBC. So what's SBC the same as? Wait, what? Do I have an SBC instruction? Oh, I do. Right, so these are weird SBC things. (6.9) and E9 are official, so I probably already have these in. So if I find usages of this, oops, yeah, 6.9 and E9. I've got E9. I don't have 6.9. (6.9) is definitely an ADC. Oh shit, wait, what? SBC E9 EB. What? ADC SBC 692 what would that have? Right. Yeah, okay, because SDC and ADC are the opposite, so it should be in this ADC type 69. And then E9 should be here, and then EB should be here, except EB, E9 and EB add 255 minus I. Yeah, okay, so this is just EB. Cool, C3. The read, write, modify instructions, increment, rotate, have few valid or Vertex modes, but these instructions have 3 more. In some cases, it could be worth to use these and ignore the side effect on the accumulator. So C3 is a DCP. C3 is a DCP. Equivalent to a DEC value, then a compare value, except supporting more addressing modes. Alright. So let's find our decrement and then our compare code. Cool. So bit instructions will probably have our decrement. Decrement memory by 1. And then compare, which is CMP, right? So decrement a value and then compare. Yeah, okay. So what are they called? DCP. Rock on. Which is just an instruction. It's going to decrement and then compare. Then compare. Okay, so the class method is literally just going to be this, and then this, decrement and then compare. Cool. Alright, let's get our DCP modes going then. So combination instructions, so same thing as before. DCP, which we should, oops. DCP, DCP types. What are our DCP types? This. Cool, so what do we actually have? So we start with indirect X. And then we go D for 0 page. Then we go A for absolute. Indirect normal. Which does indirect normal even exist? No, it doesn't. Just bland d comma y, indirect y, dx is 0 page x, zero page x, 0 page x, absolute y, which we've got here, and then absolute x, which we have here. Cool, so let's change all of these to DCP, and then let's copy this, so C3, C7, CF, D3, yep, it's going to be DX, D7, DB, DF. Cool. So that should be all my DCP types. Instruction results not expected. Yep. How many instructions do I have now? Must be around 200, right? 196. You okay? Yeah, let's keep going. So what doesn't match? Our P doesn't match. Right. Okay, so what's our self.expected P? It's 100. And our self.actual P is cpu.statusreg.toInt. 228. Let's cast both of them to binary so we can compare them. Looks like the most significant bit is not set. Alright. What if I did this? Bitwise ORs with the binary of cpu.statusreg.toInt. What if I just did this without the binary? Don't need that. Yeah, that's the one that's different. It's the 7th bit. Cool. So what's the 7th bit? Let's look at our status reg, and that is our negative bit, set to bit 7 of the last operation. So we did set it to negative. Wait, our one has it set to negative, and their one does not. So DCP is a decrement, then a compare. So I'm willing to bet it just uses the compares thing. Compare. So that's the negative bit. Well, let's see. Return. Oh, I actually don't know. What am I doing here? Why did I copy that? Compare. Right, because this literally inherits from compare. And then sets the carry bit. So return compare.write. Does that fix it? Hey, I'm new at programming files. Can you tell me how to save all of this? Okay. That's an interesting question. So Python in programming in general, or Python, or the easiest way is going to be to read some tutorials online, start using Python, and in particular to download an IDE, which is going to be an integrated development environment. So it's basically programs that are designed to help you code. So PyCharm is one of these, which is a free thing you can use by a company called JetBrains. So if you go and you download PyCharm, that'll help you through a lot of the setup and starting up of programming things and how to save and program. A lot of it becomes easier when you use something like PyCharm. Hopefully that helps a bit. Instruction not found. Yes, that did work. So I just needed to return that value instead of the super. Yeah. That was silly. E3. Right, what is E3? Nope. I thought I had all the nops. Alright, where are instructions? Nop types. E3. Apparently I missed one. E3. Wait a minute, E3 is an ISC. Oh, no, I just can't read. It is an ISC. Okay, that makes sense. So what is an ISC? Equivalent to an increment and then an SBC value, except supporting more addressing modes. Okay. So let's do that, what we just did again. So DCP. Decrement, then compare. I mean, this could just be return the updated value. So we get the updated value, and then let's just call return compare dot write. Instead of copying this code. Hopefully that'll work. Yeah, that does. Probably shouldn't, because this should be this. And then compare with the value. Cool. So I should do that with the other one that I wrote, which was a LAX and a SAX. So this should really just call LDA and value, and then tax. CPU memory address value. This should return sax, oops, Control F, sax. Yep, that did its own thing. Jump RTI, what was I up to? Oh god, store A, store Y, and EOR, ADC, SBC. What was I doing? DCP. Yep, so update and then write, and then now I'm doing ISC. Cool. An ISC, which is just going to be an increment, then SBC. So increment and then SBC. So let's find SBC. Let's copy this. Let's go back to SBC. It just needs these things. Which are probably what it's already got. Yep. So increment. So updated value equals increment dot write CPU memory address and value. Yep. And then we're going to return we're going to return SBC dot write CPU memory address and updated value. Cool. I think that works. Which just calls ADC, yeah, whatever. Alright, so what ISC types do we need? I believe it's going to be the same as what we were doing before with DCP types. Except it's going to be ISC. Not disk, but ISC. And my understanding is DX, DA, DY, DX, AY, AX, yep. So it's going to be exactly the same, except these are going to be ISC. And these bits are all probably going to be offset by some value. E, 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 F, 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 F. Yep, so E, 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 F, 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 F. Cool, so that should work now. Cannot import name stack push. Yeah, okay. So this is going to be because in base instructions, I'm now going to be importing something weird. Yep, because I import tax. So I'm just going to move this to here. Whatever. Bit instructions. Where the hell is register modifier from? Yep, okay. So let's just move this from below. So this one's got to exist in this class. Where is register modifier? Cool, so that will unbreak our imports. Instruction results not expected. Okay. Whew. What does not match? Our instruction does not match. So we expected an ISB, and what we actually got was expected instruction ISB. Is that just the NES test log being wrong? Does ISB exist? Alias used, ISB equals ISC. Okay, doesn't really matter. we can just call this ISB in wherever I have this thing. So let's call this ISB. Let's refactor this, call this ISB. Okay, cool. Instruction not found, 03. Alright, so 03. Let's go back to here, is a slow. So slow is equivalent to an ASL then an ORL. Yep, so these all support the same addressing modes, right? Yep, okay. Makes my life easy. Okay, instructions, base instructions. So, class SLO, just going to be of type instruction, ASL then ORL. So let's get an ASL and then an ORA, which is a shift bits. ASL then ORA. I swear I had an ORA. Maybe I just called it an OR. Right. Right. ORA types. Okay. So, same thing. So, let's go and do that. So, where was I? So, the ASL probably says the carry bit, so we just want to do this, and then we want to do ASL.write. We're just going to shift the bits, set the carry, and then return some updated value. And then we just want to return an OR. So ORA.write CPU memory address value, so on and so forth. And we want to be passing the updated value. So that's a slow. So let's implement all of them. So SLO, a slow, and a select. Cool. Let's also do the next one while we're here, because we know we're going to have to do these originally. We've done DCP, we've done ISB, RLA. I don't think we've done. Nope. So let's do that. So an RLA is a ROL, then end. Yep, so let's do that as always. ROL.write. Does this return something? Yep. And does and return something? One presumes that it will. Does indeed. So there's RLA. Let's do this. Find okay, so RLA, RLA, RLA. There's all the RLAs. Let's do an RRA. Same thing, except it's going to be slightly different. Check that we haven't done an RRA. Nope. RRA is going to be ROR, then ADC. It's going to be brutal. Cool. So instead of RO that, we're going to do ROR. And that's going to return a value. And then an ADC. ADC. Which is also going to return a value. And is going to modify the V. Cool, so let's implement RRA. Sick. Slow. RLA, RRA, slow. We haven't done SRE. Last one, I think. SRE. Which is LSR, then EOR. Holy shit. Okay. LSR, then EOR. Does LSR return a value? Yes. Then EOR. So this is not going to be modified. And then let's make our last things, which are our, what's it called? LSR? SRE. And SRE types should all be called SRE. Okay. Duplicate instruction bytes, that's a great point. So ISB types. So C's, then E's, then these are going to be 2s and 3s. For which thing is this? RLA is going to be 2s and 3s at the front. So these are 2s, these are 3s. RRA is going to be 6s and 7s. 6, 7. Slow is going to be 0 and 1. 0s and 1s. And SRE is going to be 4s and 5s. So these are all going to be 4s and these are all going to be 5s. Okay. Boom. Instruction results not expected. Fair enough. More instructions. We're going. Instructions results not expected. What is wrong? P match and A match. Okay. And what's my actual A? 34. Alright, so which thing is this? It's an RLA indirect. Print hello Pandy. Print hello Papa Shots. Welcome. We are currently struggling through knee deep in unofficial opcodes for the 6502 CPU. which is the CPU that the NES uses. I think actually at this point, we might have, how many instructions do we have? CPU.instructions. We have 231 out of the 255 instructions. Oh shit, getting there. But one of them's not working, so let's figure it out. RLA indirect X. So let's just look at this line in the log. Let's see if it gives us anything. Yep, this is it. 2345. So it's saying we should be looking at memory location 47, which should give us a value of 647, which should print A5. Yeah, okay, so what is an RLA? So let's put a breakpoint here. Let's see if we hit it. So cpu.pcreg. Yep, so we're at the right instruction. And an RLA, ROL, and then AND. ROL, and then AND. Cool. Alright, so we're using indirect addressing, which means that we're going to have to, so what is it expected to be? 1607. What are we doing? 45 offset by X. So how do we get 1607? So maybe it's already been done. So is this 1607? Yep. So we're looking at the right memory location, and the value is A5. 165. Yep, so we're at the right memory location and we've got the right value. That's good. So this is right, this is right. Right, so what's our updated value? Is 102. And then we want to AND that. What do we expect the thing to be? Expected A, I think if we go to here, is going to be 2, and we actually return 34. Okay. So we want it to be 2, and we return 34. So what's the updated value? 102. And what is return.write going to get us? A reg. So the value is 102. The A reg is 179. So cpu.areg ANDed with updated value returns 34, which is the one we don't want, but it's the thing that we do. So what if we did cpu areg ANDed with value 161? That also doesn't work. Ooh, okay. So is that areg what we expect it to be? We expect our areg at this point to be B3, which I presume is right. 179, yep. And the AND function is definitely just meant to bitwise AND with the accumulator and store the result. Bitwise AND with the accumulator. Yep, so we're bitwise and ANDing with B3 with 179. And if we do that, there's no like order of operations, right? For this, no. So 34, 161. So this is meant to equal 2. It's the only thing that I can guess is that this write function is probably working. Therefore this updated values thing must be wrong. So wait, we get a value of 34. We want cpu.areg ANDed with some value to equal 2. So what is updated value? 102. So what if I did it with 101? 33. So what if I did it with 70? Well, that was a really good guess. Yeah, so this is what I want it to return. mp.uint8 of 70. 2. So I want this updated value to return 70. So what does ROL do? So ROL shifts all bits left. Yeah. So what's the value I'm passing into it? 165. So what's the binary of 165? Equals that. It shifts everything left, so up. The carry is shifted into the bits that are on the original bit 7 is shifted into the whatever. Yeah, so we lose, so let's do 165 shifted by 1. So it's going to be 330 and the original bit 7. Yeah, so 165 minus 128 shifted by 1 should give us off by 174. Yeah, okay. So let's start debugging this properly. So I think the problem is in the ROL. So what's the A reg without the shift? Without that, without 7 is 51, which we would expect to be value minus 128. No, we wouldn't. Value ANDed with 128, 127. So expect to be 37. That's 51. What is this? What does this equal? Hang on. So RL shifts all bits left 1 position. The carry is shifted. I'm a noob to programming. How long have you been doing programming? A while now. Probably roughly 10 years. Maybe I've been doing it seriously for around 7, I think. So a while. Well, in terms of my life, I guess. Yeah, I spent 5 years doing a degree, and then I've been doing other stuff for 2 years or so. So around 7 years, I've been doing it pretty seriously. Still can't figure this stuff out, but all right. So for some reason, we're shifting the A reg instead of the value. So now is that actually what we want to do? ROL shifts all bits to 1 position. So do we use value in here? So the value should be the A reg. That's what we would expect. The value is not the A reg. Right. So if instead of this, let's get rid of all this crap. If we did value without this, updated value, original. So what if we did that? So in this case, our A reg doesn't actually equal our value. This equals 74, and end.write, that thing is going to equal 2. Sick, so that's the right thing. So where was my AND instruction? Because that was implemented incorrectly. No, my ROL was implemented incorrectly. So ROL, anything like it, probably like an ROR, should use value instead of A reg. Compare, that's fine. A reg. So let's do value without 7. Yeah, okay. So I think now my shifts should do that. Wait a minute. LSR. Oh no, this should just be value. Okay, here's all my shifts. So A reg. So LSR, value that 7, value ROL. Cool. RLA is still not expected. What's not matching? Because our P is not matching. That's fine. So what's our expected P? No, expected status. Oh yeah, expected P versus our status reg. What are the odds that it's going to be the most significant bit? And let's do bind of this bitwise ANDed bitwise exclusive ORed with CPU with self.expected P. Yep, so that's the most significant bit that looks like it's on when it's not meant to be. The most significant bit is the negative bit. And we're looking at an RLA instruction. So let's go back to our RLA instruction. We're saying we have set the negative bit, but we didn't actually want it to set the negative bit, which is interesting. So updated value ROL.write. So we're going to need to find out what is setting the negative bit. Shift bits. Then we're returning and dot write. So that's the negative bit. So that's the negative bit in here is whether the value is ANDed with that. Is whether we set the negative bit. So that's resolving to true. So presumably if I come back to my RA thing, something's going to equal true. So that's true at the start. And then what about updated value? Being mod with that. False. What about and.write being mod with that? False. Okay. Data value is 2. Return value. Status registered update. Does it set the negative bit? No, it does not set the negative bit. Right, and the reason for that, yeah, okay, I actually need to set these things to set their own negative bits. Oops, alright. So carry bit and overflow I think are set automatically, but for these ones, so for slow, we want to set the negative bit and the 0 bit. RLA, same thing. RA, same thing. This is going to be the same thing. Cool. That didn't work. Steppity, updated value, return value, step in. This should equal false. Does equal false. Right, so we're hitting another RLA somewhere else. Okay. Warning overflow encountered here with my ADC. Oh, we're sending it on RRA. What's an RRA do? Yeah, okay, so we're almost certainly. Right, okay, let's look. See what we got. So the p match is the only thing that doesn't match up, and the difference is the least significant bit. The least significant bit is our carry bit. 1 if the last addition or shift resulted in a carry, or if the last subtraction resulted in a borrow. So we expected it to be set, and it wasn't set. It wasn't set. Yeah. And there's the carry bit. So RRA. Let's go to here. Presumably there's only going to be one of these. Yep. RRR and then ADC. So what's my updated value? Let's also find out what my PC reg is at the moment. Let's check the test log. Put that into hex. Let's copy that value. EA, no, boom, here's my RRA. So we're meant to look at 45x, which is meant to be 0647, which if I put into hex, should equal 1607. Yep, so that's the memory address we're looking at. And the value should be A5, which if I had to take a guess, would be 165. Yep, so we're looking at the right value in the right memory address. Presumably the value in the A reg is correct as well, is B2. 178, correct. Okay, so we expect something slightly different here. We expect the overflow thing to have been set, but it wasn't. And I did notice in the log that we did actually overflow. So let's find out why it didn't catch it. So presumably when we go to here, updated value is 82, we still haven't overflowed. Let's jump into our ADC. So result equals cpu.areg 178 plus value. So areg plus value is 4, and that has resulted in an overflow. Right. Now the thing that we actually get here, let's put base instructions over here, is that it should equal 5. So there has been an overflow. Now how do we check the overflow? If value and areg have different signs than the result, set overflow. So presumably this is false, when it should be true. So that's kind of an interesting one. So if I do this, 4, if we make this .mp.uint8, now when I go to here, no, a lot sooner it's already failed. Overflow encountered, and if I had to guess, we're not doing that correctly. Yeah, so we're not detecting overflows correctly. So what passes this? Result equals 105. We haven't done an overflow, right, okay, so. Yeah, okay. So what's the areg 105? Mm-hmm. Yeah. So when we do overflow, runtime warning, overflow encountered. So I wonder if we can catch this. And if we can use that to set the overflow reg instead. Boom. Boom, boom. So I kind of want to catch this when it happens. Mm-hmm. I don't really want to ignore them. So for some reason this... you know what, I bet it is. Let's find out how many deb... 1, 2, 3, 4, 5. So 1, 2, 3, 4. So our value is 128 and our CPU.areg is 127. So result equals 0, presumably. Yep. So this is the 1, 1, 2, 3, 4. Cool. So what happens here? Is actually just going to be result. I don't really want to silence them. With warnings.catch warnings. Well, let's see. If the value and areg have different signs than the result, set the overflow. So this is 127, this is 0x80, or 128. So we're pretending that they're signed, but they're actually not. The way we treat them is unsigned. If value and areg have different signs than result. So all we're doing here, this in binary, right, is just going to be to check the 7th bit. Is the 7th bit activated? And this is saying exclusive OR, and then exclusive OR. CPU.areg. So the result is 0, so it definitely doesn't have it on. And CPU.areg doesn't have it on. And value doesn't have it on. So ADC, 6502 ADC. So this is something, one of those really difficult instructions. Where I'm just going to have to look it up, because it feels like we've implemented this incorrectly. Two's complement, okay. Is that it is set if the result of a signed addition or subtraction doesn't fit into a single byte. That is, the result overflow occurs if it's greater than 127 or less than a negative 128. The symptom of this is adding two positive numbers, which we did, and getting a negative result. 0 considered a negative result? No. Yeah, so 80 plus 80 equals 160. 80 plus 80 equals negative 96. Right. Formulas for the overflow flag. C6 XOR C7. If the carry into bit 7 is different from the carry out. That's difficult. Holy crap. So I think this is the one that I want. If A bitwise ORs with the result, ANDed with value, bitwise OR with the result, ANDed with 80, set V. So it looks like this should work. I don't know why it doesn't. Okay, so what's this? Hey, for reals. 1, 2, 3, 4. Step. So that, which is true, ANDed with that. ANDed with 128. Right, so this is going to equal false because the CPU.areg is 127. Yeah, so the CPU.areg is positive, but the value is the maximal negative value, and therefore has the same. So let's go with int 8. Let's see what these are actually. So mp.un8 of the CPU.areg is going to equal 127 of the result, which is 0, equals 0. And then a value is going to equal negative 127. UN8. Oops, they should say int 8. But I would guess this would say negative 128, sure. Yeah, okay. So wait, mp.int8 128 is negative 128. So 129 should be negative 127. Oakley dokley. That makes sense. So if value and areg have different signs, so maybe the reason is, what if I did, so this is always going to be the same, right? It's going to be 127. This last one is going to be, we want this to be true, which means these all have to be true. 128. And this is 128, so this is true, but CPU.areg ORed with the result. Alright, what's my PC reg? Copy value. Let's see what values are meant to be here. ADC 7F. Yeah, which is 127, right? Let's assume nothing. 127, which is a positive number. Morning, coming from Marinot. Not quite. I'm up to 230-ish instructions. Here's a question for you, Danny. I am back to ADC overflow code, which has stopped working when I'm now doing ROR instructions, basically, or whichever, the combination instructions. It's yep. I'm having a struggle. So basically, let's see where it breaks. Lots of instructions. Here we go. Array indirect. Yeah, okay, I don't care about this. I care about the ADC, yeah. So the areg is 178. Value is 82. And the thing is on. What about bool CPU? I guess. I'm just taking it off this site though, which seems to suggest this. Yeah, which is what this one suggests as well. So I'm unsure why this is wrong. Because this is going to return 5. Value plus. What if I did this? Yep, so that's going to return 5. And it's definitely overflowed. But this is true. This is false. And then this is true. What's ending up wrong? I'm not setting the overflow flag when the overflow flag should be set. And the reason is that value ORed with result doesn't set the 7th bit. The reason being, I guess, that result is 5 and value is 82. So they both have the same sign. Hence, the overflow is not set. Because the result actually, overflows back into positive numbers and value is always positive. So value is positive and areg is negative, and then they create a positive value, but that's not surprising, so the overflow flag isn't set. But they actually overflow 255, you know what I mean? I'm gonna try. Indicates the sign of the num has changed improperly. So there's overflow if you had two positives, there's overflow if you had two negatives. You can't get overflow when adding two numbers of different signs because the range doesn't allow it. Yeah, I mean, this is because I'm not actually using... I'm using just unsigned integers, not signed integers. So nothing is negative, it's just two complements. Your code looks the same as mine. Yeah, I'm not quite sure what's going wrong. This is potentially what's going wrong, is I'm being passed in the wrong value. But I'm pretty sure if I keep going here, everything else matches except the P. Yeah, so when I've called, where do I call it? Kill me, so many instructions, SLO, RA, and here. So this RRA is an RRR, then ADC. So potentially my updated value. In mine, I think result is a cast to a byte. Result is cast to a byte. Yeah, mine wraps as well. So this, so this is a cpu.areg is an mp.uin8. Value is an mp.uin8. And I cast this manually to an mp.uin8. So it does, hopefully that makes sense. I've started using NumPy to wrap all this, wrap all these things. Oops, did I set a breakpoint at the wrong one? Instructions, combination instructions, base instructions. Let's get rid of all this crap. Alright. Where's it breaking? It's breaking on ADC now. Ooh. Yeah, so if I do that, which is casting that to an mp.uin8, then it's gonna that's gonna blow it up as well. So let's just jump through some of these. So results 105, 107, 255. See, 255 is fine, right? I've already done that. What if I did np.uint 8 is a possible value, it's already wrong. Yeah, it definitely is, but I don't think so, because otherwise I'd get other things from the register being wrong. Not sure where you are on the log. Yeah, it's fine. Yeah, so this still equals 255, and overflow is going to equal true. Sure. 255. 0. Here we go. So we have overflow here. The result is 256. Ah, shit. Okay. So here's, okay, maybe this is what we're doing. So this instruction doesn't overflow I haven't made this overflow. Ah, this is why. Yeah, you might be right. I haven't made this overflow in an attempt to, I catch it down here. Right, so when I call this through that RRA thing, value is being passed in as a UN8, but when it's not being passed in as a UN8. So let's make it mp.uint8 a value, mp.uint8 of this thing. Right, now when result comes out, it'll be wrapped. This is fine. And now I just need to change my carry logic to check whether a carry has been done, which is if it's wrapped, right? Yeah, so I'm going to always cast it to mp.uint8 now. Okay, so this makes sense. This makes sense. At some points it wasn't being passed in correctly. So can I do this? With warnings, catch warnings, warnings.simpleFilter. Action. One of error, ignore. Which one was it? Runtime warning. How about always? All warnings will be ignored. I want to catch him. I don't think you need to go over 255 to set the carry flag. I just do this. Carry equals result ended with 256. Ah, so do you not wrap it in byte before? So is result of byte length when you do that operation? Because won't that always be false if it's a byte? Or do you do turning a result into a byte after you do that carry set? Because this is probably going to be what I should do instead of what I'm doing here. I think result is always a byte. Okay. Yeah, okay. So what you're saying is, hang on a second. What you're saying is just check down here. Instead of result greater than 256, we should just do result ended with 256. You might be misremembering. Yep, fair enough. That's fine. Do. So if I do this, result is 105. This is definitely bad. Yeah, it's an int and then you cast it to a byte later. I think that's what it's got to be. I think it's got to be an int and then you've just got to and I'm just going to set this to result ended with 256. So the byte of that, mp dot, bool of that. Accumulator plus value plus carry, yep. Carry equals result and 256. Overflow equals that, yep. Accumulator, yeah, so you cast it to a byte at the end. The reason's going to be that 1 and 0 that you return from that carry function is not bytes, and therefore it casts the whole thing to a not byte, which is what I had happening here. So really what I need to do is not cast it to a byte at all, but just have it be an int. Ensure that it's an int. Result. cp.areg, done with the result. Yep, value done with the result. And then set the overflow. And then instead of doing this, I can just do this. And then I cast it to a byte down here. Now the only question is I might need to change this into a none. No. Sick. That works. Yeah, so for some reason in ADC you have to not have it be, I don't know, you have to not have it be wrapped. Then when you're doing these calculations, then you return it wrapped in a byte. That's interesting. Can't find memory owner. Cool. So where am I up to? How many instructions have I done? Shitloads. Alright. Can't find the memory owner. Why would I ever hit that in a thing? What location am I at? 16405. Hex of location 4015. So let's check that out. Boom. Nestes reference guide, and let's go to the memory map. Memory map. Let's find out what's going on. What did I say? 4015. Yeah. APU and IO registers. Ruh-roh. So what are my current memory owners? RAM, PPU, ROM. Yeah, so I need to make an APU or something. 2000 to 2007. NES APU and IO registers. So which one has the APU? It's registers to 4000, 4013, 15, 17. Are you kidding me? Okay, let's just say the APU owns them for now. So 4000 to 4001F. Yeah, okay. So let's just copy the PPU. Let's make it an APU. 4000 to 4001F. And let's add self.apu equals APU. equals APU. Okay. Let's do that again. Can't import name APU. Bet you can. Why can't you import name APU? From helpers import numbers, sure. Yeah, okay, so something. Am I crazy here? Have I done something different? I know what I've done. I think when I did this, type APU. There's probably some circular references in here or something. Actually don't know why that is. I think if I do this, that's going to be more likely to work. Alright, import order. Cool. How many instructions have I done so far? Let's find that out. A look to will be working mostly. 231. I'm getting there. Are you at C8 6B? Am I? Yeah, I am. You're basically done with the CPU. Only a few LDAs, store A's, and RTS left until the end of the log. Fucking sick. That's awesome. List indexes. I'm out of range. Yeah, okay. Alright, well let's smash them out then. Why am I out of range here? That's weird. Store A 4015. Yeah, that looks like the one. Is there a reason that 4015 isn't mapped? 401F 4015 falls within that range, right? Position minus memory start location. Ah, I know what I've done wrong. The size is actually not 8. The size is 20. I presume that's in hex. Yeah. List index out of range. Wait a minute. I'm done? Is that what that means? Holy shit. List index out of range. Okay, so when self.index is greater than len of self.lines. Am I done? I haven't implemented all the unofficial instructions, but greater than or equal to. Self.lines. Self.index. Yeah. So wait a minute, what's the last thing that I did? RTS. Yeah, these are the last lines of the log, right? I'm done. Jeez. Alright. That's pretty sweet. Does this mean I've finished the NES test log, Danny? I mean, this is the end of the log, right? I've made it.
I'm done. I was up to here, C68B, and that was just because I hadn't set the right amount of memory for the PPU. But, yeah. Sick. Alright, that's pretty good progress. Now the fun stuff starts. Yeah. 231 instructions. So is there a reason that there are only 231 instructions? Do the other ones just not exist, or? I mean, like, what's XAA? Can't help you anymore, I'm just at a wall reading about the PPU here. I'm going to have to start doing that. Alright, cool. So some of these are like super unofficial, not even in this test log. What happens if I run main? Oh my god. I'm now in a loop. I'm running Super Mario Brothers. Somehow. Presumably. Something is happening. SCI, CLD, load A, store, load, TSX. Yeah, and then we're just branching. NES test as the UI. Oh, fair enough. I didn't know that. If you run it in a working emulator, it lets you see a menu that... Okay. NES test. Oh. Yeah. So how do I run it? I've got the NES test ROM, and it's saying just set it to... Does it use the PPU to draw the UI? Is that what you're trying to say? Because that'd be pretty crazy. Damn. Alright. Cool. Once you've implemented the PPU, you can run the NES test ROM. Yeah, I see. I see what you're saying. You're kind of running it. So whether you set the program can do to run the GUI, or is it just something that happens while you're running the automated mode? Yeah, absolutely. Use the reset vector, fair enough. Reset vector is a standard location in the ROM. Interesting. Contains the place to start the PC. Cool. Reset vector at FC to FD. Fair enough, so I haven't done any of this stuff. But these are just, right, these are just cartridge space locations. So you're saying that in the ROM, the reset vector will be stored there. as much as I have no idea what's going on. Yeah, emulation still confuses the heck out of me, to be honest. Shashwap. Shashwap. Yeah, I'm basically just as lost as you. Thank you. This is a good stream to listen to, I hope. Correct. Sweet. Okay. So presumably if I look at the NES test ROM, which I've got loaded up here, if I go all the way down to FFFF NES test, because everything is mapped, isn't it? So this would be 8FF or something. Oh, but we loaded, okay, yeah. This is a bit 4FFF? Yeah, so everything's 0, so where does it stop? Here. So we load this in at 4000, and it overlaps. Anyway, this is I think another time, another day. I think I'm probably going to stop here now that I've finished the CPU. And by finish the CPU, I mean run the NES test. I'm sure the CPU is far from finished. Fixed at the end of cartridge space. Right, so the size of this. So if I look at BFE0 minus 20, I should find the IRQ. BF. No, so this goes up to 1, 2, 3, 4. But then it's all mapped around. Isn't the ROM memory is duplicated around C? Jeez, I have no idea. Anyway, it'll be in there somewhere, I suppose. You just want to read the 2 bytes from FFCC. Am I crazy that this file doesn't have an FFCC? Or am I just getting offsets wrong here? Because it starts at 4000. From RAM location. Right, so wait, it expects me to set the RAM to that? Sample RAM map? Not RAM map, I want CPU power up state. I need to take into account the header as well. Yeah, okay. So, right. That comes back to our header code. It all goes through the same map. Do. PRG ROM, CHR ROM. Flags. Crazy. Right, the value is C004 in the ROM. CW4. And we start at C000. So this. Wait a minute. Subtract 4000 to find it in the file. Bin taken RAM cartridge goes through the same map. Right, okay, yeah. So is that in this RAM somewhere? Or is it literally set from the header and from the power up state? I am quite confused, unfortunately. Oh well. It's in the ROM somewhere, sweet. Okay, so I'll just need to determine based on various offsets and stuff like that where it is. Let me think about this. Boom, 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 boom. Yeah. My test ROM. Yeah, so CPU dot ROM dot get there we go, yeah, plus 16. C0. Yeah, so it'll be there somewhere. C004, that looks like the value to me. Cool. No, it should just be that. C004. I guess I automatically offset my ROM by the header, if that makes sense. Yeah, just load the ROM, read the 2 bytes from FSCC, set the PC, correct. You actually don't need to do any of this math unless you're trying to manually find it in the ROM file. That's it. Boom. So, let's do that. Why not do that? CPU. So what do I set the CPU PC reg to at the moment? I set it to C000. And this is telling me that it's C004. So I just need to minus 4 from that. Right, so C000 is for an automated test run, and C004 is for the other one. I see. Like when your PTU is done. Yeah, 6, so if testing we want to do, testing we want to do that, else self.pcreg equals mp.uint 16 of self.getMemory at the interrupt vector, which we know is 0xFFFC, 2 bytes, load ROM, args.test, so since we're testing, should come through to here. Then we're running our main ROM. It should come through to here. and this should not work. Yep, because this needs to be turned into a bytes or something, into an int. So I think from bytes, I want this. So probably, oops. From bytes of that soft.pcreg equals that. So cast it to a byte once you read it out of there. Let's do that again. And this should hypothetically return me the correct thing. Sweet. 1075. What if I just do this and test that it returns C004 for when I oops. Test from false. So this should return 49156. So the hex of this should be for C004. That is correct. Okay, so we now set our CPU reg based on the IRQ vector. Or if we're testing, we just set it to 4000. Sick. Alright. I'm actually going to leave it there then. That's quite good. Alright, let's quickly go through what we figured out today. So, finishing all NES test CPU instructions. So we changed our implicit addressing class to be called implied addressing, because that's what other things use. We created a basic APU, which just stores some memory locations. Anything in the CPU? We have something that now reads them from either the reset vector or from the automatic run. Nothing really exciting. We changed the pattern for NES test a bit to deal with a edge case a bit better. We added a few more modes for arithmetic instructions. We added all the combination unofficial instructions, so LAX, SAX, so on and so forth, ISB, DCP, SLO, as well as fixing up some of these helper functions. We had some small bugs with them that only became apparent when we did combination instructions. Sweet. Yeah, just renaming. We've added around 80 more instructions here, something like that, which is pretty good, because that gets us up to 231, which appears to be all the NES test uses, so that's kind of nice. And it helped to verify that our other instructions worked correctly. Yeah, again, added another 20 NOP instructions here, just because NOPs are used everywhere. Cool, so let's commit this. Let's give it a tag. Let's do all that jazz, and then I'm going to wrap it up. So tag episode 10. Some nice ordering. And we're going to push that up. Alright. Sweet. That's going to be it. Thanks everyone for coming and watching. I appreciate that. And yeah, I presume I'll stream probably once more this week. I'm trying to do twice a week and just keep it a bit consistent like that. So yeah, thanks for watching. If you have any questions, whatever, shoot them at me. I'll stick around for a minute or two, and then I'm gonna head out. Thank you for watching, Sigma. I appreciate it. It's yeah, it's always fun to do. I'm making good progress, I think. Stuff is finally happening. which is rare sometimes. Looking forward to the next one. Thank you, Danny. I'm looking forward to it too. It'll be good to get off these instructions. Might not be able to watch it live. Aussie's in your weird time zone. Yep, fair enough. I also blame my time zone. That's fun. I'll struggle along. It's always nice when I'm stuck in a hole and someone that knows what's going on comes along and helps me out. So it's good to have people around, but if you can't be around, you can't be around. So I'll push through. Happy birthday for the other day. I hope it was good. Even if you had to go into work and struggle with that. NES ROM header, I should probably do that at some point. Read that in properly. What else can I quit? No, that's right. Yeah, that's awesome. And yeah, I'm impressed that you made it. Well, I presume beyond where I'm up to, but made it through the CPU without anyone coming in and helping you out. I have been leaning on people helping me out a bit, so which is good. It's been a good learning experience. So hang on, if I run main now, instantly dies. That's good, isn't it? Yeah, whatever. Break instruction hasn't been tested. I'll have to figure that out. It was a struggle, but you're basically exactly where I am now. Sweet. So I'm guessing for me the next step is going to be cleaning up some of this register stuff and the interrupts, breaks, stuff like this. And then probably starting on doing the PPU. I'll probably do the PPU first and then head on to the APU, I suppose. I haven't really thought too far about that. Yeah, looks like I might need to fix my break instruction. Because I don't think there are any breaks in the NES test thing, which is probably why that hasn't been tested. Anyway. Thanks for all for coming and watching. It's good fun. It's always fun to make some progress and, yeah, have some people following along. So, yeah, I'll see you all sometime later this week. PPU, APU mapping. PPU will get the most visible results here. Yeah, that's what I'm hoping. Get a nice little Mario level visible. That's really the dream. I need to figure out how I'm going to do graphics actually in Python. I haven't really thought much about that. Probably pickle it or something if it still exists. I could just do an OpenGL wrapper or something. It should be pretty simple. Yeah, see you next time, Danny. One thing, I'm actually going to have to go back and do a bit of speed as well. I haven't thought about that at all, and it looks like I might need to make this a bit faster, but whether or not that matters, I guess we'll see.